by Farhad Barbhuiya and Palak Bansal. Farhad is currently working at product security engineer at Honeywell and holds around 5 years of experience. He has delivered over 2,000 hours of training at various organizations, ranging from educational institutes to government bodies. Joining him is Palak Bansal, whose enthusiasm is deeply rooted into the mission of protecting the digital realm. Together, they will be discussing on macOS security, DYDL insert libraries injection challenges. So let's welcome them.
Can you keep?
Hello, everybody. Hi. I know it's been a long day with full of knowledge. Let's continue to learn more with this particular session where Farhad and I are going to speak on macOS DYLD library injection. So as already introduced, my name is Palak and I am working at Honeywell as a product security engineer. I have an experience of close to 5 years, and today I'm here excited to share more knowledge with you on this topic. This is my colleague Farhad.
Hope I'm audible. Yeah, so my name is Farhad Sajid. If you have been into some other conferences as well, somewhere, you might have encountered me. So I've been presenting it for some while, and already I have been given some introduction about myself. So let's get started with it, and we'll connect if you want more introduction about me, right? Okay, yeah, Palak, go ahead.
Okay. Thank you, Farhad. So I'm sure we must have used Mac sometime in our life, here and there. If not used, must have seen it, right? Today's topic will be about the DYL library injection. Even before we delve into the part of the injection part, let's try to first understand what are the DYLD libraries. And even before we go into that topic, I want to ask to all of you, are you aware about the DLL injections or the object file injections? Yes. Okay. I see few nods here, which is good. So what we see in Windows, this is the counterpart of the same in Mac, right? Where we deal with the dynamic libraries that are loaded during the runtime of an executable or an application. So basically, this feature allows to indicate a process that is going to be run to load the dynamic libraries and when the executable is launched. Most of the times, we don't even come to know about this process because it's seamless. It happens on its own. However, if say we encounter some error, wherever the dynamic library fails to be linked, then we realize, then there is a frightening error message saying, unable to load the library, it's DYLD, unable to load the binary, some error of this kind, and then we realize that the linking process fails. Now, I'm sure, we must have thought once in our lifetime that why Apple products are so expensive, right? But have you ever thought how secure are they? Let's try to understand few of the security features that Apple platform provides, in current time. Now, Apple's operating system software is designed with security at its core. This design includes secure boot, secure enclave, and various other features that we see on the left side of this snap. This snapshot has been taken from the official website of Apple. On the right side, we can see that there is the root of trust, which forms the basis of the secure boot. Now, there is a boot ROM code, which is the root of trust and forms the root of chain for the secure booting process in the Apple platform. Now, this secure root of trust is accompanied by a dedicated AES cryptographic engine, which is responsible of securely and efficiently generating the cryptographic operations, carrying out the cryptographic operation, and then there is a secure memory storage. Then there is the secure enclave, which is a secure subsystem of the main Apple's, which is integrated in the Apple system on chip itself. And it provides a layer of additional security which makes sure that the sensitive user data is intact. It's not compromised, even when the application processor kernel is compromised. So the secure enclave does not have its own secure storage, but it has the mechanism to keep the user data secure in the attached storages, which comes on the system on chip provided by Apple. Okay, so this is about the root of trust, secure boot, and secure enclave. Other than this, there is kernel integrity protection, which makes sure that after the initialization process, the kernel code is not changed, it's not compromised with. The KIP bit, the hardware which is used to set the KIP is logged so that it's not manipulated after the initialization. Similarly is the fast permission restrictions. This comes with the Apple A11 and Bionic. So basically it includes a CPU register that quickly restricts the permissions per thread. Moving on, next is the system coprocessor integrity protection. This is similar as KIP. There is a coprocessor that has a firmware which performs quite important tasks. For example, it initializes secure enclave, like I told. So it's important to make sure that the coprocessor firmware is also secure and it's booted securely. So the mechanism that is employed with the kernel integrity protection is also the same as system coprocessor integrity protection. Okay, and the last two are the pointer authentication codes and the page protection layer. Pointer authentication code is nothing but to protect the exploitation of memory corruption bugs. This basically prevents the modification of function pointers and return addresses. Then comes the page protection layer. It basically prevents the user space code data to be, prevents it from modification after the signature verification is done. So yeah, these are pretty much the security features that are provided by the Apple platform on the hardware level. Now let's try to understand about the secure boot process with the Apple Silicon chip. So like we see boot ROM, again this left side snap is from the official website of Apple. The first is the boot ROM. It is the root of trust. This is where the secure boot process starts, and it's like the zeroth step of the secure boot. So boot ROM is responsible for validating the LLB, which is the low-level bootstrap signature. Once the low-level bootstrap LLB is launched, it then verifies the signatures of the system paired firmware, which can be, so the Apple chip is not only responsible for verifying the firmware or the software, but also the policies, the security policies that are implemented. So LLB then validates the system paired firmware signatures like storage, displays, Thunderbolt, etc. It's also responsible for checking the local policies. Now these local policies is a text file. These are user-defined policies that can be used during the system boot up or during the runtime security policies. The difference between these security policies validation is that the signature validation is done locally by the secure enclave. It is not done by the Apple centralized server. So the signing of these local policies is done locally. And the validation also happens locally with the help of the secure enclave processor. Then once the LLB validates the local policy signature, it passes the control to the iBoot stage 2 signature according to the local policy. Now this iBoot is also responsible for checking the local policies. The information about it has received from the LLB. That was the step prior. After that, once the iBoot validates the macOS paired firmware, boot kernel collection, and the auxiliary kernel collection, this information also it receives from the local policy that has been given to the iBoot from the LLB part. Once all these validation happens, then the system is securely booted up and there is a full-fledged system to be used, available for the use. There is another feature called SSV. It's a kernel mechanism that is used to verify the integrity of all kinds of data, be it code or non-code. during the runtime, and it rejects any data which is not properly validated during the runtime. So this is the secure booting mechanism with the Apple silicon chip that has been there in place right now. Okay, so looks like Apple already provides a lot of security features that are already in place and that we as a user already take benefit of them. Now let's try to understand what is this DYLD libraries and what are this feature and what are the loopholes and how can they be leveraged to perform these injection attacks. Okay, so to understand this technique, let's first delve into how the application loads a dynamic library. macOS, like any other operating system, be it Linux or Windows, has the feature to load the dynamic libraries using a dynamic linker. So basically, that dynamic linker is used to load the dynamic libraries, which are called dilibs. Say I have an executable or an application that I want to launch, and that application needs to, it has some dynamic library linked that needs to be launched along with the launching of that executable. So macOS will basically launch the Mac-O loader, which is responsible for loading the app code data into the address space. It also will load the dynamic loader into the process and pass the control over to the dynamic loader. Now, this dynamic linker has a macro header. Now, this macro header contains essential information that will be needed by the system in order to load that particular dynamic library when the executable is being launched. So this macro header contains particular information about that dynamic library. For example, the name of that dynamic library that needs to be used, or the list of the dynamic libraries that are dependent libraries and that needs to be linked as part of the executable. So there is something called install name, which gives the complete path of that particular dynamic library that needs to be loaded. This all information will come as a part of the macro header, and there will be some load commands that will be read by the dynamic linker in order to load those particular dynamic libraries. So as you can see, there are these load commands which are part of the macro header are nothing but the data structures on the left side, as you can see. The important load commands that we need to take care right now are lcload dylib, lcload weak dylib, and the lc re-export dylib that are highlighted. I'll try to explain the meaning of each one of them. So lcload dylib, basically it specifies the dynamic library to be loaded at the time of runtime, and if this particular load command is being set, then the dynamic library needs to be loaded, otherwise the executable will not work. It will not be executed. So if lcload dylib specifies a dynamic library to be loaded at a runtime, it needs to be loaded, otherwise there is an error thrown if that dynamic library is not found or loaded adequately. Then is the weak dylib. It means that it specifies that a library is being weakly linked, which means even if the library is not found or properly loaded, the application or the executable will still end up running. Lastly, the last load command specifies a dynamic library to be exported by the binary or library. Okay, so like I told, every binary has a install name. Install name is something which will be used by the dynamic linker to identify that particular library, and this information it will get from the macro header, which will be coded by the developer inside the executable as a part of macro header. So this install name will also contain the information about the path where the dynamic linker has to see in order to find that particular dynamic library. Now there are 3 path prefix, as we can see here: executable path, loader path, and R path. Executable path is basically, it contains the path to the directory containing the main executable. So if I want to launch an application and that application has the dependency on some dynamic libraries, this executable path will be the path of that particular library, particular application or the executable that is needed, and that has a dependency on other dynamic libraries. Second one is the loader path. Now, like I told, there is a macro header that is needed to get the adequate information in order to load those dynamic libraries. This loader path will be the path to the directory that will contain those macro binaries, the information that is needed by the dynamic linker. Lastly is the R path. So R path is a variable. R path is the variable that will contain one or more paths towards the dynamic libraries. LC rpath command is again a loader command that will be present in the macro file, macro header. That LC rpath will be taken and will be replaced by the rpath and will tell the dynamic linker that, okay, these are the paths of the dynamic libraries that needs to be loaded in order to execute this particular application. So, yeah, these are the three path prefix that needs to be defined inside the macro header. Now, the developers can use various tools in order to define this rpath. One of the tools is the install name tool that can be used in order to define this rpath for the dynamic libraries. So,
All right. I believe there were a lot of hardcore terms, right? And many of the terms were newly being seen for the very first time for most of you, right? And yeah, that is one specific reason behind the thing. That will be that to buy iPhone, you have to sell kidney, and to buy macOS, you have to sell both of the kidneys. Still, it doesn't come, right? I'm not sure what's the price of kidney going on. But anyway, at least you now know the terms, right? And what's the best, if you are getting to know about the terms, later on you can look into it. But yeah, you will have the slides, and they have, because these terms itself are, it took us a lot of time to understand for ourselves at the very first go, because they are very much complex, and Apple likes to keep things very complex so that even though hackers can't figure it out what it is doing in the nutshell. And that's one of the predominant way of Apple to achieve security. But again, it's a very hardcore security to talk about. Okay, now moving forward. As of now, I guess you have understood a bit about what is DYLD and what is dylib in the nutshell, right? Okay. Now, if you see, try to compare this with the concept of DLLs that you encounter in Windows, or shared object that you encounter in Linux. Okay, try to correlate it, and then it will become more easier for you. Okay, rather than just focusing on those hardcore terms, it will be there, but try to correlate with it. And I will also try my best to make sure that we go with that particular pace. Okay, so for every dynamic library that is out there, okay, so dynamic library, that DL, compare it with that. So in context of Mac, they have something called as install name. Okay, now what is the use of this install name? This install name identifies the library to the dynamic linker, which Palak was explaining about. Okay, so when you basically see this, okay, this is the install name and this is the dynamic linker, and then the path that Palak was mentioning, executable path, R path, and all, then only dynamic linker will fetch from that particular path and present it to that of the actual executable binary, right? So once that particular process is done, the next thing, in order to go ahead and load and execute it, the first process that up till now what we were discussing was linking part, how we are linking it with that of the dynamic library. Once linking has been done, next thing, what do we need? After linking, if you remember the core concept of OS, linking, then loading, then compilation, then execution, or the binary itself, right? That is the flow, right? Correct me if I'm wrong. Okay, so linking done, the next process is loading, correct? So let's talk about the steps that are involved in loading. So for every dependent library, okay, dependent library, when I say, there is a separate file which will contain the additional code and resources, what actually the DLL file does. They are just additional code or additional resources that the main executable always look forward to in order to just import them during the runtime when it is as required, right? So here what happens is the DYLD will check if the dependent library is already in the DYLD shared cache or not. Something related to memcache or caching way of web caching that we see, right? That if it is already there, why not fetch it from there? So same thing happens here also. Okay, but that is not the context with when we talk about Windows or Linux, right? There is no caching mechanism for shared object or this thing, what do we call it as, DLL files to be picked up. Don't confuse it with the temp that you see. That is a different concept. Here we are specifically talking about caching of that particular DYLD library as a whole, okay? So here, as I said, the DYLD check will be happening whether that particular dynamic library is there at the DYLD shared cache. So DYLD shared cache is what? It is a pre-built cache, which is system provided, specifically meant for your dilibs and the relevant frameworks, okay? Now, where can you find this DYLD shared cache, right? So that's the path, system, library, DYLD, and DYLD underscore shared underscore cache underscore, whatever the binary is. So each and every application that you will have in Mac, then, so that's why I gave the asterisk because, so for example, let's say Sublime text you have, okay? So it will be system, library, DYLD, DYLD shared cache underscore Sublime, whatever the application name is. So if it is, let's say, App Store, so underscore App Store. So I hope everybody got the context what I'm talking about. So that's why I gave it an asterisk. So first, that will be the search path. Now, can you guys think what can be done here? We know the path, okay? What can be done here? I gave you a hint. Try to correlate it with cache poisoning. What can be done here? Can we go ahead and create a shared cache file, which is a poison file, means a malicious file, and rename it and put it over there? Can we do that? That would be first test case that will come if you are doing a pen test or an assessment, right? That will be the very first thing. Okay, keep that thought in mind. We'll talk about it, okay? Okay, so that is there. Next thing is, if in case it is not there in that particular location, if the library is not there in the shared cache, then what it will do is that, remember the LC load command that Palak was talking about? Then it will go for LC underscore load command to check what is the dilib load command path, okay? So that will be there. Now over there, again your R path will again come into the picture. Linker, there were three different types of path, executable path, R path, and another was there, I forgot. But here specifically it looks for the R path only, other two are not taken into consideration, okay? So LC underscore load underscore asterisk again, because it will be application specific, right? Whatever application you are dealing with, it will be application specific, followed by the dilib. So if that is declared, it will basically look for the configured R path, right? So DYLD will search for the for the dependent library during the runtime. One is in the embedded path or in the executable itself, right? Now, if you look into these two things that I've just discussed, can you guys try to recall and see how it is similar to something we do when we are doing DLL injection? We have some specific paths, right? First, it goes to the executable path, then after that, application, then program data, program, then system32, program x86. So they have that hierarchy, right? The travel that it looks through that, okay, first I'm going to look the DLL here, then here, then here, then here, then here, right? That is, there is this flow if people have done DLL injection. So does it correlate something similar to that? If you look, right? It does look something similar to that. Yeah, good. So next, if still we are not able to find the dilib file or the where the dilib file is residing, then in that case, what will happen is the dynamic loader will search for the dependent libraries in the base standard location. So what is the base standard location? So these are the base standard location, that is user local lib. user lib, and system library frameworks. Okay, these three are the base locations where it will look for the dilib. Okay. Now, in case there is a missing dependency or a mismatch with its versions and they are not marked as weak, the launch process is terminated immediately. One point to note, they are not marked as weak. Remember one particular load command that Palak was talking about, lc_load_weak dilib? So if you are explicitly mentioning that that particular dilib is a weak load, then yes, that will be included, right? But apart from that, if you're not explicitly mentioning it, developers don't do that anyway, okay, because of the lot of guidelines, frameworks, and policies and all. But yeah, if you are not explicitly doing it, because if you do that, it will be easier for an attacker to go ahead and run a grep command and check for this particular weak lc load command, okay? So developers often won't do that. So you can remove that from your test case, but just for your information and knowledge purpose, you should be aware of that, okay? Okay. So, okay. So I was saying that how will you check for this, whether a dilib injection is possible or not, right? O-tool, have you guys heard about it? If you have done iOS pen testing, O-tool, you might have, if not, so there is this tool called O-tool, similar to if you try to compare it with, you can use it for debugging, for runtime analysis. It can do a lot of things. It is similar to that of GDB and LLDB, if you guys have used that. So it is similar to that, but it is specific to Mac, right? So if you use O-tool followed by -l and give the name of the binary over here, you can see I gave ZenMap, which is the macOS version of the GUI version of Nmap, right? And there I was specifically grepping for this particular load command called lc_load_dilib. So here you can see I found lc_load_dilib in 4 instances, right, along with the path, if you see. System library framework core foundation, user lib system, system library frameworks again, and the top one is user lib object ca.dilib, right? So this is the very first way to how you go ahead and check for this thing, dilib, whether the dilib is there or not, or something you can grep or not, okay, get hold of. Certain times this haven't worked for me, specifically when the M1 came into the picture, it didn't work for me for, I don't know, for some strange reason. So there is a very well-known researcher called, he goes by the name Patrick. He has created his own dilib hijacking scanner, right? So it's kind of an automation he has done. So that works pretty well. So that is also something you can look into, right? So if any dilibs have @rpath, so over here we don't have that particular thing, but what you will see is that if like you have these keywords called command size, name, timestamp, current, compatibility, and all, similarly you will have a keyword called rpath in case the rpath is declared, right? So if any of the dilibs which are there has rpath declared, so immediately you have to look into which load command, lc_rpath. Remember that Palak was talking about? lc_rpath, okay? So that will be the second thing that you have to look in case there is a rpath coming as part of your, this thing, output, whether you are using O-tool or whether you are using that tool created by Patrick for scanning for dilib hijacking. Even though that gives you the full, this thing, output of whether the dilib hijacking is possible or not, but still you will get in the output that whether rpath is declared or not, okay? Okay. Now here, if you are thinking that all the complex and hardcore parts were up till now, welcome, this is going to get more complex now. We'll try to make it as simple as possible, but it's going to get complex, for sure. So this is the newer code base of how, so specifically when Apple chip came into the picture, so M1 series and all, right, S series and all. So all the Apple series, when it came into the picture, how, so earlier dilib injection when the Intel series was going on, it was very straightforward and simple, very simple. Okay, I have a screenshot I will show you. It was very straightforward and simple. But for us, we are the main context or the main idea behind showing this presentation was why it has become difficult in the later series, that is the M1 series or the update. M series, not M1 specifically, M series and the T2 chips. So this is the code that they have implemented in order to restrict or restrain the exploitation of dilib injections in mass. Okay? So what they have done? So first thing they have done is something called as SIP. You remember the very first or second slide where we were talking about different protection mechanism, KIP, SIP and all, FPRR and all. So system integrity protection we were talking about. And the reason behind why we were talking about is because system integrity protection plays a role when patching this DYLD library injection methodology technique. Okay? So let's understand how this SIP verification happens. So there is something called as CSR check. Yeah, you can see this line of code, bool use using SIP, CSR underscore check, CSR allow underscore task for PID. Okay, so this CSR check is basically checking if the CSR allow task for PID bit is set, right? And if it is set, what it will do is that it will go ahead and basically check for flags. Okay. So there are multiple flags you can see, CS ops status, right? And then it will go for this thing, CS underscore restrict. So it will basically check for these flags. This flags basically comes from something called as CSR configuration, okay? Now, in case this CSR underscore check, sorry, not CSR underscore check, it is, CSR underscore check basically returns Boolean value 0. Then what will happen is that immediately that binary will not load that dilib. So they have mandated it that CSR underscore check should always, not should always, if and only if it is binary bit is coming to 1, then only we are going to proceed further for rest of the checks in order to load that dilibs. Okay? It's not just that, okay, you are getting the bitmap value as 1 and you will be able to go ahead and load the rest of the dilibs. It's not like that. It is just one of the first checks. Okay? Now, that basically will define or not define, determine if SIP is enabled or not, right? Earlier in the Intel series, the Apple was trying to achieve the similar way of CSR underscore check with something called as CSR underscore restrict, okay? So if CS underscore, sorry, not CSR, CS underscore restrict is enabled, then only it was saying that, okay, we'll allow you to go ahead and load the dilib into the program context, okay? Now, the next thing is that, okay, the next thing you will notice over here is if flags and CS underscore require underscore LV is restricted equal to false, library validation equals to true, and then there are tons of other codes. What it is doing over here is that it is checking for two things. One is called CS underscore require underscore library, and another one is called CS underscore require underscore LC code. These two are called as signing flag. So in case you have done iOS pen test, you might have done this Uber app signer. Sorry, is it Uber app signer? Yeah. Which basically signs with a dummy, this thing, code signing certificate and provisioning profile to an IPA file, whichever you provide, right? So that is something you do it as an attacker's perspective. So once you do that, what it basically does in the nutshell, it basically goes ahead and sets the signing flag. And what determines the signing flag? The CS underscore require underscore LV and CS underscore required underscore LC code. So they are the one which basically checks whether the main binary which is loaded is first of all is having code signed or not. If yes, then whether the same code has been used to sign the dilib or not. Because it doesn't make sense, right, that your dilib is signed with some other code signing entitlement and the provisioning profile, and your main binary is signed with some different code signing entitlement, right? It doesn't make sense. Both has, if it is from Google, it has to be signed from Google. Everything has to be signed from the Google certificate or the code signing certificate, right? So that is the one which basically looks into it. Okay. So that was related to CSR check, SIP check, and code signing. Next is AMFI. So AMFI basically is Apple Mobile File Integrity. Okay, so AMFI, if I put it very simple way, is the one which is responsible for setting up process restrictions, how the process should behave, what should be the memory context where it should run, how much memory it should take, how much CPU memory and the GPU memory and the process working bits and the private bits should be set. Everything is basically determined with the help of AMFI. So this is the one. So um, so earlier there was something called as MSCF, which was basically extended in the newer version with Apple Mobile File Integrity, right? And AMFI is the one which enforces SIP and code signing. So SIP and code signing are the mechanism to validate and verify the binaries and the dilibs, right? But to implement them and enforce them, AMFI is the one responsible for them, right? Also, MFI checks for second thing that is called as whether restricted segment has been defined or not. When we say restricted segment, what do we mean by that? Simply put, restricted segments are something like depth or non-executable bit which you have, if you guys have learned about memory corruption vulnerabilities. The protection mechanism that we have is data execution prevention in the context of Windows, and no executable bit, NX bit, that is set to true in case of Linux, right? So what they basically do in the nutshell, they basically go ahead and restrict a particular set of memory segment as restricted. So if in case you are trying to inject on that, that will simply crash the program with that sysseg or some other kind of error, right? That is what it is in the nutshell, right? So here, this basic MFI is responsible for checking whether the binary has the restricted segment set or not, right? Another thing now comes is that we have the release build and we have a debug build. So whenever you are going ahead and basically building the final build, it will give you two options, whether you want to go with the debug build. It will always give you this thing, output. One is the debug build and one is the release build, right? Now, in debug build, oftenly, whenever you are doing a testing as a developer's perspective, this will be set, build for testing, right? So if build for testing is set, this compiler flag is set, the reason is so that we can debug it, right? That's why, because it will be testing, so we can check for all the errors and whatever issues that are coming. So if this flag is set, then of course you can debug that particular dilib or the main binary itself. And as said, it will be 0 on the production builds because that will be release build and we don't want anyone to go ahead and debug it, right? Okay. Next thing is, so this is this thing. Check DYLD policy internal. This is the pseudocode because Apple, it is completely created by Apple, and one of the researcher went ahead and dragged and dropped it in IDA and was able to get a pseudocode. It's not the actual raw code, right? So if you look into this, so there are multiple registers that has been declared RX, R13, R14, RX, RBX, CX, and all. So there are multiple registers over here, and if you try to just look into it and try to understand what it's trying to do, is first of all is that you will see macOS DYLD policy at path. Remember about the local policies that we were talking about at the beginning of the session, right? Then next is the macOS DYLD policy environment variables, policy fallback path, and library interposing. So this four, basically what they do is that they will basically check whether the environment variables are correctly set for that particular application to run. Second is fallback. In case there is some errors or some issues coming back, what should be its fallback mechanism so that it doesn't lead to any kind of issues or injection-related vulnerabilities. It should come back to its some stable state or should close the program, something like that, right? So that's what is defined in fallback path. And library interposing means if there are similar two libraries in the same two different locations. So let's say user system lib and user system framework, right? Same libraries are defined. In that case, which one to give more priority to, right? So that is basically declared over here. So AMFI will basically determine the flags by verifying the calling process, right? And yeah, macOS DYLD process collect state verifies the code signing properties, which is the entitlement I was talking about. Okay, now, thankfully, the complex part is over. Let's get to the bit of an hands-on part. So here, a simple code, which is basically having a constructor, and this is a If you look into the code, it's doing nothing, but we have a constructor defined which is taking 2 inputs, right? And it will simply print a dilib constructor called from whatever the location with the argument, and it will log a particular error in case there is with dilib constructor called from whatever it is. So this is simple proof of concept script which will basically be considered as a dynamic library. Okay, so it's a dynamic library. Okay, think of that. You have .dll file which you create with MSF Venom, right? So it's a simple that only. Okay. And this is a simple hello world program. As the name suggests, you can see it's the simple hello world program. Now, this is the one that we did in the Intel. Okay. So if you look, simple compilation with GCC. Okay. So yeah, simple compilation with GCC. We have a.out and all, and we have our binary ./welcome. So if we execute our welcome binary, we see welcome to dilib injection simple demo, which is the expected output which we're looking into. Now, if you are going at, because in that code we have not explicitly introduced RPath or anything as such, so in case you want to include this thing, any dynamic library during runtime or during initialization, you can basically mention dyld underscore insert library and give the name of the dyld library that you want to insert, followed by the binary in which you want to insert. So dyld.simple is the first code that I was showing you, and ./welcome is the simple hello world or welcome code itself. And when I do that, you see, dilib constructor called from ./welcome and welcome to dilib injection simple demo, which basically suggests that our dilib injection worked perfectly, right? This was with Intel, okay? So we tried to do with some production binaries. This is a MacOS binary in Apple. So we tried to go ahead and basically inject that particular dilib sample file that we created to the binary itself. So binaries are usually located in application macOS.app, contents macOS, followed by the name of the app, right? So we tried to do that, and you can see it basically went ahead and got executed, and you see the macOS file got opened up, right? Okay. Similarly, and when we always look forward if we can see some logs, right? Because generally with binaries, what will happen, production level binaries, what will happen, you won't see that message that we were getting with the that C file or C program, sorry, right? So how can you do so? In Mac, you will always have something called as console, okay, which can be used for doing logging of entire things that are happening over the Mac, okay? So here you can see in one of the event, it will show you the dilib constructor from this particular path has been called. So if you are encountering this, that means that dilib injection has happened for that particular binary itself, okay? And we did the same thing for ZenMap. It was working perfectly. But when we did for Sublime Text, it was not working. Sublime Text is similar. I think most of you might be aware of that. If not, it's similar to that of a Notepad++. It was not working for that. And we did that on this M series. Now we started trying to analyze, like, why is this happening? Then we came out, okay, let's try to recreate that proof of concept, what Sublime Text was actually trying to do. So here, what we did was, first of all, we went ahead and basically changed the permission of the welcome binary to that of a root, okay? Sudo chown root welcome. And then we basically set up the setuid bit, okay, SUID bit. Once we did that, you can now see the owner is root, and read-write executable you guys are aware of, but if you see S, that basically means that it is a setuid program, right? A setuid bit has been set. Now when I execute the program ./welcome, it says welcome to dilib injection, which is supposed to be. But now if I do this, see the difference? That dilib is now not getting loaded. Earlier it was getting loaded, right? Okay. I went ahead and removed the setuid bit, so you can say sudo chmod -s. And now when you try to execute that, now you see it's again able to load the dynamic library which I am giving, right? So one of the first restriction here is related to the setuid bit. And now try to correlate with the concept of MFI and SIP that we are talking about. They were looking into those particular restricted segments, setuid bits and all, and code signing, right? All right. Here we have set up again a simple C program where we have set up a restricted pointer, right? Now, we went ahead and basically checked whether that particular program has restricted bit set or not, and you can see there is a restricted segment set, right, over here. So you can use size -xlm and the binary name restricted. So you can see there is a segment which is restricted. That means that program does has a restricted segment. Now, if we try to go ahead and basically look into, we have to compile it with that set create restrict underscore restrict, so that that restricted segment that we have set comes during the compilation and the restricted segment gets created. And when we try to execute it with our dilib proof of concept, it basically gives you an error saying restricted segment program. Again, that is what MFI basically was helping us try to do. Lastly, the code signing part. So here we just created a self-signing certificate, right? The name of the certificate is dilib demo. And so we basically went ahead and copied our welcome binary to welcome-code sign, and we basically did a code signing to that particular binary. And once done, if now you can see it, if you try, once you have done the code signing, you can verify it with this command, code sign -db, name of the binary, and it will basically give you the information, what is the signature size, when it was signed, info.plist, and all those information, which basically verifies whether that particular binary is signed or not, okay? Now, if you try to go ahead and basically do d underscore insert library equal to dilib.simple./welcome-code sign, you will basically see, again, it is not getting loaded. And that is actually coming from the SIP, which was basically validating the code sign, right? Okay. Now, before moving to the next slide, how can we defeat this? Any idea? Because since that setUID bit was set by program was mine, I was able to remove and set the setUID bit. So in the production application which you are downloading from App Store or from some other places, it will be very much difficult for you to go ahead and play around with the binary to remove the setUID bit or place it in. Okay, so that you can skip. Coming to the restricted segment, again, either you have to reverse engineer it whole to remove the restricted segment. Again, that increases the complexity. Lastly, coming to the code signing. So code signing part, somehow you need to get hold of the code sign entitlement, which was used in order to sign that particular binary. Then only you will be able to sign the malicious dilib. And once you sign that malicious dilib, then only you will be able to load the malicious dilib code, right? So that's what Apple has came up with in order to restrict and protect dilib injection being exploited in mass in the newer series of that's the Apple series, right? So yeah, that's all for this session. Hope you guys enjoyed it and liked it. It's way above the time, so if you have any questions or anything, I will be near around. Please feel free to reach out to me, and if you have any questions or you want to connect. And thank you very much, and yeah.